Hey guys, and welcome to my tutorial on correctness proofs. So a few weeks ago, I showed you guys how to design tests using Quick Check for testing your programs. So testing is a fantastic way to get some assurance that your programs work the way that you expect them to. However, a test will never tell you for sure that your program is going to operate properly. In order to actually know for sure that a program will give you a output given a certain input, you need to write a proof. But before we get too into that, let's talk a little bit about how we reason about programs. Okay, so how do we really understand what a function does? So let's consider the following function. Sum is a function that comes from the prelude that we could define like so. It'll take a list of A and return an A, where A is anything that's a member of the num class. So basically anything we can add to get it here. So if we want to reason about sum, we go about it in a few different ways. One thing, we can load up GHCI. Okay, and just start trying out random values of sum. What's the sum of the empty list? What's the sum of the list with one thing in it? What's the sum of the list of 2, 2, 2? Okay, we just start entering different values and try and figure out what it's doing by whatever outputs it gives us per input. Another thing we could do, which we've been doing as we've been studying recursion, is we could pick a random input, just like we were doing in GHCI, but instead of having GHCI develop it for us, evaluate it for us, I should say, we could try and evaluate it manually ourselves by hand. So we would say, like, what's the sum of 2, 3, 2? So what happens here? So the sum of 2, 3, 2 is going to be the same as the sum of the list of 2 colon 3 colon 2 colon empty list. Okay, so keep in mind that this is just special syntax for this. So when we call sum on this is going to pattern match to x colon x's, where x is 2 here and x's is this list here, the list that's left over there. So this is going to become 2 plus sum 3 colon 2 colon empty list. Okay, and then what's going to happen now? Well, now we have to evaluate this sum here. So we keep it moving. And this now becomes 3 plus the sum of just 2 empty list. What are both these? Okay, and now this becomes 2 plus, and now this is just the sum of the empty list. And then once we get to the empty list here, this is where we can no longer map to this pattern. Okay, there's no colon anymore. So now we have to go with this case, which is 0. So we just plug in 0 there. Okay, and then we just add this all up, which, because I passed elementary school math, I know is 7. But both of those methods kind of involve just picking random input and only trying things out on that random input, seeing what output we get. What if we want to try and reason about how our program behaves in general? Okay, how would we go about doing that? Well, let's start off by considering our function from before, and considering that it is pattern matching with 2 different cases here. So the way we could look about this is we could get 2 equational definitions out of this. We could say whenever sum has an empty list, it's equal to this. Whenever sum pattern matches to x colon x's, it's equal to this. Okay, we have like 2 kind of equations to be working here. We'll call them definitions. And we'll give them a name. This will be sum.1 and this will be sum.2. So now that we have those definitions, let's consider a property that we might define for sum. So just like when we were doing tests, we might define a property and say, okay, if sum works properly, then the sum of any list with one thing inside of it, okay, so this is a list that's only going to have one thing inside of it, x, that sum is going to be equal to just that one thing, okay? So if we were testing, what we would do is we would get quick check to just generate a bunch of random values and see if it works for those values. But that doesn't show us if it works for all of the values. So the question is, now that we have these equations, can we basically use equational reasoning, so basically math, to then prove that this property always holds, that this thing on the left-hand side is equal to this thing on the right-hand side? So how would we do that? So let's start with the left-hand side, the sum of x, okay? So we know by the definition of the list, okay, so I've shown you before that this is how a list is defined, by this two brackets x is defined as x colon the empty list. We have the sum of x colon the empty list. And if we look at the second equation, sum dot 2, that says whenever you have x colon x's, that becomes x plus sum of x's. So then we could use that equation to get x plus the sum of the empty list. Then, by equation 1, okay, we have the sum of the empty list is equal to 0. So now, where we have the sum of the empty list here, we can get equation 1 here, right? And now we also just know from math that x plus 0 is just equal to x itself, okay? So we could just write integer arithmetic here. There's a specific math theorem that you could reference technically. This would be like the identity of plus. But for now, let's just write, whenever you have to do math, integer arithmetic. So now this is really cool. We've used those two equations and some equations that I kind of just know to be true, like plus 0 is just x here, and the definition of the list, to actually prove that sum of the singleton list of x is equal to just x. But before we just call it a day here and say, all right, we can prove stuff now, let's talk about certain pitfalls that we might run into where our proof might not actually work for the practical application of the function. So for one thing, let's look at how I mentioned that this step is integer arithmetic specifically. Okay, so why did I do that? Well, remember that with floating point addition and subtraction, you always wind up with some amount of floating point error. So generally, even if this was a floating point number and you added just the literal 0, you will be okay in assuming that, okay, this is still just going to equal x. But if you had a variable that you would assume would be close to 0 or so on, it's not going to be a given that x plus that variable is actually going to equal just x. There might be some floating point error to take into account there. Another pitfall has to do with definedness and termination. So to consider what definedness and termination are, let's consider the function here, fact, okay? So fact of 0 is equal to 1, and fact of n is equal to n times fact n minus 1. So let's say we call fact on a negative number, like -1, or really just any negative number. What's going to happen is fact is going to infinitely recurse. It's going to keep calling n minus 1, and it's never going to end up at 0. So fact is not going to terminate, we would say. We would also say that fact is not defined on -1 here. So if I have a function, like this never end function right here, that on a positive number will just return that positive number, but on a negative number, it'll just count down forever and never terminate. So let's say I'll give this a try. Never end 1, this returns 1. If I give it never end -5, we're just going to keep waiting here. Okay, and it's just never going to end. So we press Control C to get out of this, to interrupt it. So we would say that never end doesn't terminate on any negative number, and it's also not defined for any negative number. On the other hand, let's say we have a function like mod here, okay? Our built-in, it's the same as our built-in mod, but I'm showing you how you could go about defining it here. And Mod here, if you give it, let's say I have to load up GHCI again, store lib. So mod here will always terminate for any given input. But let's say you give it anything that's mod 0. You'll get an exception divided by 0. So here we would say that mod is not defined for y equals 0. Okay, so even though it terminates for all of its input, it's not defined for all of its inputs. So just a special note here for when we're proving stuff, that when we have an equation like this thing equals this thing, these proofs don't hold, those equations don't hold for anywhere where it doesn't terminate or it isn't defined. And if you were to take an advanced class on doing formal methods, so this is an advanced class on proving programs, you would go out of your way to first prove that any of these situations actually do terminate and are defined, and then you would use those equations. So just something to keep in mind here, that this is a pitfall that you could run into where something isn't defined and your equations don't work out quite the way you were hoping them to. So if we're going to continue talking about proofs, we should first talk a bit about logic. So if you were to take an initial course in logic, you would first learn about something called propositional logic, which is basically just algebra, except instead of using plus and minus and times and division over numbers, you'd be working over bool, just true or false values, and your operators would be and or and not, and something called implication, which is basically the logical if then else. So let's do a little overview of propositional logic by implementing all of the propositional logic operators in Haskell. So we'll start off with the AND operator. So there's a binary operator. It's going to take two Boolean values and return a Boolean value. The way AND is going to work, we can define it using pattern matching. So we're going to say if both things are true, then it returns true. Any other scenario where whenever there's a false involved, will return false. Okay, so AND is basically saying if both of these things are true, we're going to return true. Okay, so if we were to try and evaluate a function, okay, like or just let's say an English statement, like the sky is blue and grass is orange. Okay, is this true? Yes. Is this true? No. Is this whole statement true? No, it's not true, because you're saying that this has to be true and this has to be true. Okay, so if either of these things are false, the whole thing becomes false. What about or? Okay, so this all evaluates false. What about or? So or is also a binary operator. And the way we're going to define or is we're going to say if both things are false, then it returns false. Otherwise, in any other scenario, when there's at least one true, then it's true. Okay? And looking again to, let's go back to this statement. And let's take a look about what this statement would mean if we're saying or. Okay? The sky is blue or the grass is orange. So this would be true. Okay, this whole statement ends up being true. So why is this? So when we're doing an or, what we're saying is if either these things are true, then the whole sentence becomes true. But if both of these things are false, that's going to be the only scenario where this thing becomes false. So let's try now the not function. So this is a unary operator. So it's only going to work on a single Boolean and then return a Boolean. And we can define it also with pattern matching. And what not does is it basically just flips whatever argument it's given. So we say not false is equal to true, not true is equal to false. Okay? So if we had not the sky is blue in English, what would this be equal to? This would be equal to false, right? Because the sky is blue. The sky is blue. So this is true. But then we're saying not of it. We're saying that the not sky is blue. So in English, we would usually write this: the sky is not blue. However, in math, we tend to write things like this: not the sky is blue. And the whole sentence then ends up being false here. So finally, what about implies? So implies is the trickiest one to wrap your head around. So it's another binary operator. So it's going to take two inputs, two Boolean inputs, and return a bool. And so let's say we have implies x of y. Okay, so we can do this by pattern matching again. So we could say implies true, false equals false. And then implies any other scenario equals true. So just looking at the definition of this, it's a bit trickier to wrap your head around exactly what is happening, what the intuition for implies is when taking, let's say, an English sentence and encoding it into propositional logic. So just to work through an example of what's going on here, if I were to say, if the sky is blue, then the grass is green. Okay, if I were to make a sentence like this in English, that would be the same thing as saying the sky is blue implies the grass is green. Okay, so if you wanted to take a sentence like this in English and encode it in propositional logic, the way you would do that is you would look at it this way. The sky is blue implies the grass is green. And if we look at what this statement evaluates to, so both of these things are true, so the whole sentence becomes true. Okay? Now, what if the sentence was the sky is orange implies the grass is green? This throws people off a little bit because they're like, well, this is false, right? So now this whole thing must be false. But actually, what you're saying is that you could look at it this way. If you have any statement like if false, then anything, right? It's always going to be true. Like as soon as you do like if false, then the whole sentence is true. Okay, so this also ends up being true. Okay? Because you're just saying if false, and it's like the condition failed right away. So now it doesn't matter what comes up afterwards. That's a little weird to wrap your head around, but this is the way you want it to work when you're trying to write this sentence on. You're trying to make a condition that's like, well, this whole thing only becomes false. The actual sentence itself, the statement you're trying to make, only becomes false when you say something is true and apply something that is false. So if you have the statement, the sky is blue, implies the grass is orange. So the sky is blue, this is true. And then you're saying it implies something that is false. So now you know, okay, this sentence is wrong. Okay? So the whole thing becomes false. So the way you can look at implies, like really all of these operators, is you have some sort of sentence and you're like, is this sentence correct? Is this sentence making a true or false statement? Okay? Overall. And in this case, if you're saying that the sky is blue implies the grass is orange, obviously that's not true because the sky is blue, but the grass is not orange. So this is how implies works, and it's a very, very useful tool because a lot of times we do want to express some sort of condition when we're working in propositional logic. So now that you know about concepts like definedness and termination and the operators from propositional logic, let's do a little case study. So consider the function we defined before, fact, okay, that takes the factorial of a number. So the factorial of a number is going to be that number n times n minus 1 times n minus 2 times n minus 3, all the way until you reach 0 and then just times 1. So the convenient way to define this is through recursion. We define it as n times fact of n minus 1. So if we wanted to make a property to test that the factorial is working properly, what we could do is we take the fact of n and divide it by n. And you can see right from our definition here that if we take this, okay, the fact of n is going to be equal to this right here, and we divide it by n, we're just going to end up with a fact of n minus 1. Okay? So this is a pretty good property to be testing. However, what's going to happen if we code up this property and we call it with quick check? So say we have our module here, we have fact coded up here, and we have our property that uses fact. Okay. And what we're going to do is we're going to test fact. So we could load this into GHCI. So make sure it's saved and load into GHCI. Okay, and we're going to use quick check. So make note that we've imported quick check here. We're going to call quick check fact prop. Okay, and right away you see that it fails, and it gives us exception. Divide by 0. Okay. So the way we get around this is so if you look at this, you can see first of all that we do a division on n here. So of course, this is going to give us an error when n is 0. Okay, we're going to have to divide by 0 here. So what we're going to want to do here is we could say, well, if n is equal to 0, then we just return true. Else, we return this. Okay? So the idea here is we don't want to test the scenario where n is equal to 0. We'll just say, okay, if n is equal to 0, we'll just assume it's true. Okay, we're only testing, we're only concerned if this returns false for scenarios where n isn't equal to 0. So let's give this a try. So let's save that and reload it and call quick check fact prop again. Okay. And see, it runs 2 tests. It's saying it's 2 tests, and then it gives us an exception stack overflow. So a stack overflow is what happens if you have an infinite recursion that runs long enough. It generally inside of an actual thing that does I/O, like quick check, it'll actually give you a stack overflow then. Okay, so basically what happened is it didn't terminate. It called fact, and fact did not terminate because, like we discussed before, fact doesn't terminate whenever you have a negative number. So we should update this a little bit. So instead of saying if n is equal to 0, we could say if n, okay, is less than or equal to 0. Then we just return true. So if n is less than or equal to 0, we just assume things to be correct. Otherwise, then we do our actual test. Okay? So basically what we're saying here is we're only concerned with testing this if n is bigger than 0. So now we can save and reload and run it again. Okay, and finally, now it works. Now we're able to pass the test. So the idea here is our proposition, it's a good proposition, but only for the values which fact is defined for. Okay, so we need to constrain it to only operate over the values that fact is defined for. And I did this using an if, and you'll notice that, let's say if we define our implies function again, implies This if here that we're doing, because it's an if that returns a Boolean value, okay, either true or this, can actually be replaced with implied. And we're going to put some brackets here just to specify present. Okay, so this is actually the same thing. We're saying if n is, what we actually want to do here, sorry, is if n is bigger or equal to 0, then we do this scenario. So it's actually in the reverse scenario. If we did if n is bigger or equal to 0, then this, else true. So now that we've done a little sanity check by testing that fact prop holds using quick check, so getting quick check to generate a bunch of random different inputs and seeing if fact prop still holds, let's see if we could actually prove that fact prop holds. So given the definition of fact here, we'll make two definitions, okay, to work with. So we have two equations to work with here. Let's say we have fact of n divided by n. Okay, so given the fact2 definition here, we're able to expand fact of n, okay, using this equation into n times fact of n minus 1. And then once we have n times fact of n minus 1 divided by n, we just know from mathematics, so again I'll just reference integer arithmetic, particularly since div here works on integers, that if we have n divided by n, we just cancel these terms out. Okay, so we'll just cancel this out, and we're left with fact n minus 1. And there we go, there's our proof. Simple as that. Now keep in mind, like we just discussed before, that this proof is only going to hold for where fact is defined. Okay, so on 0 and negative numbers, this proof actually doesn't work. So if we're going to prove stuff about more complicated functions, we're going to need some more sophisticated proving techniques. So the main one that we'll use for proving stuff over lists is going to be called something called structural induction. So I'll give you a formal definition of it at first. Hopefully this won't confuse you too much. I think after you see a few examples, it'll make more sense. But here we go. In order to prove a logical property, P of x's. So x's is here is some list, and P is some property, just like the property we had before for fact prop here, okay? It's something that takes a list x's and returns a Boolean value. So we're trying to prove that this always returns true. Okay? So there's two things we have to do here. First, we prove that it holds for the empty list. Okay, so whatever function this is, we prove that it returns true over the empty list. Then we prove that if P of x is true, then P of x colon x's is true. So basically we get P of x's as an assumption, something that's already true, and we prove this is how it ends up working out. So P of x's, we're going to call this the induction hypothesis. So this is something that after we've done the base case, we can just assume it to be true. Let's consider an example of this. So the reverse function on list can be defined using these two pattern match cases. Okay, we might reason about the reverse function using a quick check property like this. The reverse of the singleton list is just that same singleton list. How would we prove that that property is correct? So we could write a little proof. It'd be pretty straightforward. We would first use the definition of the list to break down what's happening here. Use the second definition, okay, so this definition right here, to expand what happens when you have x colon x's. So in this case, when it's x colon empty list, it becomes the list of x plus the reverse of the empty list. Then by the first definition, the reverse of the empty list equals just the empty list. We get the list of x plus the empty list. And then we know, the same way that we know that anything plus 0 is just that same thing, a list plus the empty list is just that same list, okay? That we have the list of x. Now, what if we wanted to have a better property, okay, to test reverse here? So an even better property to test reverse would be that, okay, the reverse of a list is just that same list. So if you reverse a list twice in a row here, we do the reverse of a list, we get the same list back. To prove this, we're going to have to use structural induction. Okay, this one isn't going to be as straightforward as the last one. So what we do is we take the base case, which is the empty list. So remember, for structural induction, we prove the base case, the empty list, and then we prove x's, knowing that the predicate of x's is already true. So we'll start with the base case, and we'll say the reverse of the empty list. Okay, what is this equal to? Well, we take this term right here, and by the first definition, the reverse of the empty list is just the empty list. So what do we end up with? Reverse of the empty list. And then we use that definition again, and we end up with just the empty list. So what have we shown here? We've shown that the reverse of the empty list is equal to the empty list. So we've proven the base case now, because x's was the empty list inside that case. Now the inductive step is inarguably much more difficult. So to get started off here, what we're going to do is, just keeping in mind what the inductive step is, we have to prove p x colon x's. And we have just p of x's as our induction hypothesis here, just known to be true. So what we need to do is prove that the reverse of x colon x's is equal to x colon x's here, okay? So the first obvious thing to do is to take this term and use the second equation to expand it. So if you remember, the reverse of x colon x's is equal to the reverse of x's plus the list of x here. Now at this point, we're a little stuck, okay? And what we're going to do is something that I've kind of been doing all along when I do stuff like eval, plus, and integer arithmetic and stuff, where I just kind of look at this and I'm like, well, okay, I need to get somewhere with this. So I'm just going to make up a rule that I kind of just know to be true, and I'll give it a name, okay? So I'll call this a lemma, all right? And what I know to be true is, so I have this term here, reverse and something plus something else. So it's like reverse x's plus something else. And what I kind of know I want to do is I want to like distribute this reverse to the individual terms inside of here, right? So how could I do that? So, well, I know that what I can do here is if I have the reverse of two terms added to each other, what I do is that you take the second term and that becomes the reverse of that term plus the reverse of the first term. So this is something that you can just think through yourself. You know it to be true. What you should really do is you should prove this property later. But for now, we're just going to assume it to be true. Okay, just like we did with the integer arithmetic stuff, we could have gone and done the work and been like, okay, let's prove this property true. But for now, we'll just assume it to be true. We'll just create this equation. It's like, well, I'm pretty sure this equation is true. We'll assume it to be true right now. And if it is true, then the proof will work. So having this equation now, we'll use this equation, the lemma, and we'll get the reverse of the list of x plus the reverse of x's. Now, the interesting thing that happens here, so first of all, we have the reverse of the list of x, and from the proof that we did before, we know that's just the reverse, that's just the list of x on its own. So from the previous proof, so you can see what's happening here is proofs that we used before or proofs that we haven't done yet, we can continue to use. So we get just the list of x here. And then we have the reverse of the reverse of x's. Now the reverse of the reverse of x's, this is the induction hypothesis. So remember, we talked about we're proving x colon x's, assuming that x's is already true. The predicate of x's is already true. So we're proving that the reverse of x colon x's is true, assuming that the reverse of x's already works. So we're able to take the reverse of x's and turn that just into x's using the induction hypothesis. And then at this point, we just need to evaluate plus plus, knowing how plus plus works. And we end up at our correct answer of x colon x's here. Let's consider another example. So consider the two functions length and take. So length, it takes a list and returns the number of elements inside that list. And take, it takes an integer, n, and another list, and it takes n elements out of that list, returning the list of just the first n element. So we get a few different equations out of this. So just like with the other examples, length and take, we get one equation for each pattern matching case. But with take, we get an equation for the empty list pattern matching take, and then for the list pattern matching take, because there's a guard here, there's a conditional, we get an equation for each scenario of the conditional as well. Okay, so for when n is bigger than 0, we get 1, and otherwise we get another. So, can we kill two birds with one stone here and try and prove a property about both of these functions? So if we take the length of x's from x's, we just get that same x's again. So to do this, we're going to need structural induction again. So let's start off with our base case here. And our base case, so keep in mind, our base case is we're going to have to get from this, where x's is the empty list, to this. Okay? So we're going to have take length empty list of empty list equals the empty list. So our base case, take length of empty list and the empty list. And then if we look back at our equations, take 1, we know that, well, taking anything with the empty list is just going to equal that empty list again, right? So easy peasy. In that one step, we've proved our base case. Okay. Now, the inductive step is going to be a little bit more complicated, but we can get through it. We're going to take now the length of x colon x's from x colon x's. So keep in mind what we have to do here. So we have to take, so now x's here is x colon x's. So we have to take the length of x colon x's from x colon x's and arrive at x colon x's. And we have this assumption that this equation here, this is our induction hypothesis, that take length of x's already equals x's. So the first thing we're going to do here is we have take this here. So we can expand the length of x colon x's. Okay, so the length of x colon x's is equal to 1 plus the length of x's by this definition, length 2 here. Okay, so by length 2 here, we end up with take 1 plus the length of x's. Now, we can expand take here using the definition of take. Okay, so if we go to definition 2 of take here, so n is bigger than 0, so we use definition 2. and we're going to end up with x colon take n minus 1 x's. Okay, so we end up with x colon take. Now we have this 1 plus length of x's minus 1. All right, so this is n in this case. So this would be n, all of this here, n minus 1. And then we have x's here. So right away, in this spot right here, you can see, well, we do some integer arithmetic here. And we get rid of these two 1s. And we just end up with x take the length of x's. Now, remember what I said, take the length of x's. This is our induction hypothesis, okay? So it's like this part here, we already know this to be true. So we could take this now and just turn it into x's. So doing that, this all becomes x's. And now we're at our answer, x colon x's. So we're done now. Okay, so before we finish off, let's just do a little recap about what we learned today. So keep in mind, evaluating integer arithmetic is okay, but it's not okay to do the same for floating point arithmetic. Okay, so over and over and over again, I used integer arithmetic. I just kind of alluded to that as being some sort of equation that we could plug in, kind of just knowing that, well, I know in math something plus 0 is equal to that same thing or something, right? We can't do the same with floating point arithmetic because of floating point error. So keep that in mind. Also, something we do, which is kind of the same of what I've been doing with the integer arithmetic stuff, is that I just create these like lemmas for trivially true properties. So over and over again, I would run into these points in my proofs, like in reverse here, where it's like, okay, I'm stuck here, and I kind of know the equation that I want in order to continue. So I knew I needed this, okay? So rather than going through the work of proving this, I just kind of said, well, I'm just going to assume this to be true, and maybe I'll prove it later, or maybe I'll just test it to be that's true, and I'll just use it in my proof for the moment. And really, I'm doing the same thing when I'm doing stuff like eval plus plus and stuff. I could have gone and looked up the definition of plus plus and written a more formal equation for it, but I just kind of knew that a singleton list plus plus x's was going to turn into this. So I just kind of took it for granted. Really, this is not the proper way to go about proving stuff, but for beginners, just learning how to kind of write proofs, this is a fine thing to do. And the idea is that you could come back and prove these things later. A good idea is also, if you're going to make these lemmas, you could use quick check to try and just check that they're correct quickly before just assuming that they work and not really giving any more thought to it. So we'll leave off here for today. This is a bit of a confusing tutorial for you guys, because it's kind of an intro to something that you really need to take a lot of time to learn how to do properly. So in order to do a good course in formal methods, you probably want to do a course in logic beforehand and really cement those ideas down, and you probably want to have a certain amount of knowledge in math and stuff. So don't be afraid if you come out of this tutorial thinking like, well, I still don't really have a very good idea of how to prove stuff about programs in general. This is just kind of a primer to how to do formal proofs and how to reason about your programs. And even if you aren't really that interested in being able to prove your programs all the time, this is a very useful skill to know, because it helps change how you reason about your programs. It probably even help you change how you test your programs, because it gets you thinking about how properties of your programs work. Okay, see you next time, guys.